A single concrete pile can the weight of up to 600 Airbus A380 aircraft. In Dubai, engineers set a world record by applying 36,300 tons of load onto a single point deep underground. This is no longer just construction. This is a direct battle against the gravity of an entire planet. But to keep these megastructures standing, everything doesn't start above ground. It begins with secrets buried tens of meters below the surface. Secrets you're about to uncover right now. Our first stop on the journey to decode megastructures is a bustling commercial site in the heart of Kuala Lumpur, Malaysia. This is the Desa Sri Hartamas Commercial Tower Project, developed by the SCP Traders Group. Looking at the scale of this site, you can see this is no ordinary civil construction. For high-rise towers or massive industrial complexes, the foundation requirements are extremely rigorous. They must be able to support loads of tens of thousands of tons in complex strata or unstable soil conditions. Immediately after the measurement phase is completed, the real beast of the construction site appears, the auger bored pile drilling rig. This is a mechanical marvel with ultimate torque. The high-strength steel spiral drill bit begins penetrating the surface soil. The drilling process is not simply digging a hole, it is a battle between machinery and geological fluctuations. As the drill goes down, it continuously excavates layers of soil, sand, and weathered rock to the surface. Typically, a primary hole will be drilled to a depth of 20 to 30 meters. However, in projects requiring ultra-large loads, the drills may have to penetrate even deeper until they hit solid bedrock. One of the biggest challenges engineers face when drilling deep is the stability of the hole walls. Surrounding soil pressure and groundwater always tend to push inward, ready to collapse the borehole at any time. To prevent this, engineers use a dual protection solution. First is the temporary steel casing. This steel pipe is lowered by a vibratory hammer to protect the upper part of the borehole from erosion and keep the mouth of the hole from collapsing. Second, for the weaker soil layers below, bentonite slurry, a special mineral mud, is pumped into the hole. This solution has a specific gravity greater than water, creating hydrostatic pressure that pushes outward against the hole walls, acting as an invisible skeleton, keeping the borehole structure stable until the concrete is poured. When the drill has reached the design depth, the process of cleaning the bottom of the hole is meticulously carried out. All drilling cuttings and loose soil and rock remaining at the bottom must be completely removed. If the bottom of the hole is not clean, when the concrete is poured, this mud layer will sit between the pile tip and the bedrock, creating a soft joint that causes the pile to settle as the building is constructed. After accepting the cleanliness of the hole, we move on to the installation of the reinforcement steel cage. These steel cages are the skeleton of the pile, helping it withstand not only vertical compression, but also bending forces from vibrations or storms affecting the building. The main bars are tightly bound with hoops to form a solid cylindrical cage structure. Lowering the steel cage into the borehole requires seamless coordination between the crane and the ground crew to ensure the cage descends vertically without striking or scratching the hull walls. Finally, the finishing step is pouring concrete using the Tremie pipe method. High-strength concrete is led directly to the bottom of the hole through a steel pipe. As the concrete rises from the bottom, it displaces the bentonite slurry and impurities to the surface for recovery. This process must be carried out continuously without any interruption to avoid creating stratified concrete layers. The final result is a solid, reinforced concrete pillar, firmly anchored to the bedrock deep in the earth, creating a sturdy support for architectural ambitions hundreds of meters high. Every completed board pile is a testament to the perfect combination of mathematics, geology, and mechanical power. Why did the engineers here choose the board piling technique instead of the traditional precast concrete pile driving method? The answer lies in two factors: environment and performance. In densely populated residential areas like this, driving piles with a hydraulic hammer would create violent vibrations that could crack the foundations of nearby buildings and create uncontrollable noise pollution. Board piling completely solves this problem by removing the soil before putting the material down, minimizing the displacement of the surrounding soil masses. Leaving Malaysia, our journey continues to Japan to witness a completely different level of meticulousness and precision in reinforcement steel handling. We are at an Asian Kogyo construction site, where engineers are performing one of the most challenging foundation tasks, installing the ultra-heavy D51 steel cage system. In construction technical notation, D51 is not just a number. It represents steel bars with a diameter of up to 51 millimeters. This is one of the largest and heaviest types of reinforcement steel used in modern infrastructure structures. Look at the scale of the steel cage being hoisted into the air. A single cage like this can weigh dozens of tons, requiring seamless coordination between heavy machinery and the skill of master craftsmen. Japanese precision is evident from the very way they align the steel cage. At Eishin Kogyo, errors are not measured in centimeters, but in millimeters. Engineers use laser alignment systems and digital measuring devices to ensure the steel cage descends into the borehole in an absolutely vertical line. Why is this so important? Because if the steel cage tilts even by a small degree, it could strike the borehole walls, causing soil collapse or misaligning the concrete cover, leading to future reinforcement corrosion. Another incredible technical detail is how they handle the joints. Since the depth of the foundation hole often far exceeds the standard length of a steel bar, the cage segments must be joined during the lowering process. Instead of using manual wire tying methods, the Japanese prioritize high-strength mechanical couplers or pressure butt welding technology. This ensures that at every position, the joint's strength is always equivalent to or higher than the original steel bar itself. Every millimeter of this skeletal system is designed to withstand immense shear and bending forces from the ground, especially in the extreme seismic conditions frequently occurring in Japan. This is not just construction, it is the art of absolute precision. If you thought foundation engineering in Japan was the limit, prepare for a real shock at the Dubai Creek Tower project. Here we are no longer talking about ordinary structures, but an architectural marvel that defies the laws of physics. To keep this tower standing firm on loose desert sand and withstand extreme groundwater pressure, engineers had to execute a deep foundation campaign unprecedented in history. The primary tool used was the hydrophrace, a specialized deep trenching machine with counter-rotating diamond cutters. It dug more than 72 meters into the ground, equivalent to the height of a 20-story building, but completely buried beneath the surface. The most shocking figure is the material volume. An estimated 1.6 million tons of reinforcement steel will be mobilized for this entire megastructure, starting from the dense steel networks right underground. A total of 145 barrette piles were installed, forming a superpowered base system. To verify the load capacity, engineers tested a single pile with a weight of up to 36,300 tons, a new world record for pile load testing. This is a testament to the power of 21st century engineering, where humans transform desert sands into the most solid pedestal on the planet. Following the completion of the ultra-deep barrette pile system, the Dubai Creek Tower project entered one of its most challenging phases, the construction of the massive raft foundation. This logistical campaign required absolute precision, described as a high-stakes, all-night mission. To create a solid base, engineers conducted a continuous concrete pour for 30 hours. The goal of this continuous pour was to avoid the formation of cold joints, weak points that could fracture the structure under immense pressure. The scale of this operation is truly staggering, with over 16,000 cubic meters of concrete pumped into the foundation. To maintain an uninterrupted flow of material, a fleet of 840 truck deliveries cycled through the site. 6 long-reach concrete pump trucks were strategically positioned around the circular pit to distribute the concrete evenly across the dense reinforcement steel. A total of 3,200 tons of steel had been previously installed, with a combined rebar length of 325 kilometers, enough to stretch from Dubai to Muscat. This is not just a record of volume, but a testament to peak thermal control and technical coordination under harsh desert conditions. Most people only notice the visible part of a skyscraper, but in reality, up to 40% of the value and the most complex engineering lie within the underground cities beneath the surface. Have you ever wondered how engineers can build a solid, perfectly waterproof basement system in just a few days instead of months? The answer lies in the cutting-edge precast technology that we are about to explore right here at Gladhar-Keller's construction site in the UK. The process begins with site clearing and excavating a massive pit to the precise depth using excavators. After the base is compacted, a protective waterproof membrane is laid before placing reinforcement mesh and pouring the foundation slab. Once the slab gains strength, the real difference begins. Instead of traditional wooden formwork and on-site wall pouring, prefabricated twin wall panels from the factory are transported to the site. Observe how engineers position and lower each panel onto precisely marked locations. These panels consist of two thin concrete layers joined by steel, creating a cavity in between. After internal partitions are installed, the ground floor slabs are also craned into position and temporarily supported by steel props. The key is the infill concrete stage, where concrete is poured into the core of the twin walls, turning the entire system into a unified and incredibly strong monolithic structure. Finally, a thick layer of bitumen is applied to the exterior surface to ensure absolute waterproofing before backfilling the site. This entire assembly process takes only 3 to 5 days, an incredible speed for traditional basement construction. To understand why these prefabricated basements achieve such a staggering precision, we must go inside the Gladhar-Keller factory in Germany. This is not a manual concrete foundry, but a fully automated production line supported by robotics. The process begins with CAD drawings, where every detail from window placements to electrical sockets is digitized. A shuttering robot cleans the steel table surface before a computer-controlled plotter draws the exact dimensions onto the casting table. The shuttering robot then places magnetic stop ends with near-zero deviation. Even the reinforcement system is automatically cut and placed by robots based on pre-calculated statics. One of the most unique features is the installation of lattice girders to link two wall panels together, forming the signature twin wall structure. Concrete produced from a quality-monitored mixing plant is distributed precisely and compacted using high-power vibration motors to eliminate all air pockets, creating a mirror-smooth surface. After pouring, the panels enter a curing chamber at 40 degrees Celsius and 90% humidity to accelerate the drying process. After just 8 to 10 hours, the first panel is hardened enough to be flipped and pressed into the second, still moist panel, creating a unified element. Once transported to the site, engineers simply use a crane to lower them into position and pour link concrete into the core. The entire process from production to installation is monitored by laser technology, ensuring every millimeter matches the design drawings perfectly. This is the pinnacle of industrial manufacturing in modern construction. To further demonstrate the power of precast technology in optimizing underground infrastructure, let's look at the installation of the Easy Base system by FP McCann. In traditional projects, constructing and finishing a drainage manhole can take up to 48 hours for concrete and mortar to fully cure. However, with this prefabricated system, the entire process from base placement to cover slab installation takes less than an hour. The manhole base features integral benching channels and connectors cast directly in the factory. Once lowered into an excavated pit with a leveled foundation, engineers use lasers to precisely align it with the primary outlet point. Connecting pipes are fitted using specialized lubricant, compressing rubber seals to create an absolutely watertight yet flexible joint. This flexibility allows for up to 5 degrees of deviation at each connection point. Eliminating manual brickwork and benching not only accelerates progress, but also ensures consistent infrastructure quality across the entire urban network. Leaving the shadows of the deep foundations, we rise to witness the presence of steel and glass giants. In Brisbane, Australia, the Sky Tower is not just a symbol of height, but a complex puzzle of engineering at extreme altitudes. Observe the perfect combination of the solid reinforced concrete core and the surrounding tempered glass facade. At this height, wind pressure becomes the greatest enemy. To ensure safety and aesthetics, the unitized curtain wall system is installed simultaneously with the completion of the lower floors. Each glass panel is not merely decorative. They are designed to withstand powerful wind gusts and continuous thermal expansion under the harsh sun. The construction speed is pushed to the limit, with each floor taking shape in just a few days, making Sky Tower the tallest residential building in the city. This is the moment where the vision of architects and the strength of engineers merge as one, redefining the Queensland skyline. To truly feel the pulse of a megastructure, nothing is more impressive than time-lapse footage. In the heart of Melbourne, the Aurora Melbourne Central Tower is rising like a living organism amidst the urban landscape. Through the accelerated lens, we can see the staggering transformation of the city skyline in just a few months. Pay close attention to the slipform system constantly moving upward. This is the heart of the vertical progression. As the central core leads the way, concrete slabs and steel frames follow closely behind. The coordination between massive tower cranes and crews working through the night creates a dance of machinery and humanity. Constructing a high-rise in a bustling city center requires incredibly sophisticated logistics coordination. Thousands of tons of materials must be lifted at exactly the right time, ensuring not a single moment is wasted. Aurora Melbourne Central is not just a soulless mass of concrete, It is the result of millions of labor hours and the most complex static calculations. As daylight fades and construction lights blaze, the tower continues to grow centimeter by centimeter. These films are the clearest testament to humanity's power to conquer height, turning dry blueprints into a towering icon that completely transforms the face of an entire metropolitan area. Hollow concrete? It sounds absurd, but stuffing thousands of plastic balls into a floor slab actually helps the building bear loads better while saving millions of dollars in materials. Let's see how engineers cheat gravity using Kobiak's plastic spheres. The Kobiak system is a smart construction solution using hollow plastic modules to replace non-load-bearing concrete in the center of the slab. The process begins by transporting steel cages containing plastic voids to the site and arranging them over the lower reinforcement mesh. Workers secure these modules tightly with wire ties to prevent shifting. The key lies in the two-layer concrete pouring process. The first layer is poured just enough to cover the bottom of the spheres, providing stability and preventing Archimedes' buoyancy from lifting the plastic units. Once the first layer reaches a specific stiffness, verified by a foot pressure test, the second layer is poured to finish the slab surface. Using vibrators ensures concrete flows evenly into all gaps around the spheres. The result is a flat slab up to 35% lighter while maintaining full load-bearing capacity. This not only reduces the load on columns and foundations, but also allows architects to design larger spans, creating spacious open areas without the need for excessive columns. Instead of rigid wooden formwork, Binishil's technology utilizes air pressure to shape buildings. A flexible membrane is laid on the ground, topped with flexible rebar in a special concrete mixture. As air pressure is pumped in, the entire structure gradually inflates, forming perfect aerodynamic curves. Once the concrete cures, the pneumatic formwork is deflated, leaving behind a sturdy architectural shell. This method not only saves 50% on materials, but also enables the building to withstand fires, floods, and violent earthquakes, thanks to its thin shell structure that distributes forces extremely efficiently. To see the true power of atmospheric pressure, look at the inflation of this 1,000-ton ammonium nitrate storage dome. The process begins by laying an ultra-durable technical fabric called an airform over a predetermined circular foundation. High-power fans begin blowing air underneath, transforming the flat tarp into a rigid dome in just minutes. This air pressure is maintained continuously to serve as a mold for the subsequent internal steps, spraying polyurethane insulation and shot-creating high-strength concrete over a reinforcement steel mesh. This monolithic dome structure is the optimal choice for storing explosive chemicals due to its absolute airtightness and superior strength against natural disasters. It is the perfect marriage between flexible materials and the durability of concrete. Have you ever wondered where the millions of tons of stone needed for these skyscrapers come from? Look at these steel jaws crushing boulders at a rate of 300 tons per hour. This is where pure mechanical power takes over. Massive stone crushing plants, the backbone of all infrastructure projects. The process begins with the installation of a 300-ton per hour crushing and screening plant, an integrated system of jaw, cone, and VSI crushers. Large raw material is dumped by trucks directly into a 35 cubic meter bunker. Here, the primary jaw crusher performs the task of breaking large boulders into smaller sizes before moving them onto conveyors. The system operates on a closed-loop multi-stage crushing model to ensure final product quality. The stone continues through a cone crusher for angularity and a VSI crusher for shaping, enhancing concrete adhesion. After each stage, multi-deck vibrating screens sort the stone into various sizes, like 1 by 2 or 4 by 6. Oversized stones are automatically returned to the crushers via feedback conveyors, ensuring not a single piece of material goes to waste. We moved to the Mbour region in Senegal to witness Fabo Global's fifth fix crushing plant here. This plant is specifically designed to process silex phosphate, a material requiring advanced crushing technology due to its high abrasiveness. Instead of traditional vibrating feeders, this system features an apron feeder to ensure a more robust and stable feeding process. The conveyor system here is designed for continuous operation even during the rainy season by replacing pan feeders with specialized conveyors. The entire process, from primary jaw crushing to secondary crushing with the CC300 cone crusher, is fully automated. To control fine dust and protect the working environment, misting nozzles are installed along the vibrating screens. This fixed crushing plant is not only a technical benchmark in Senegal, but also plays a pivotal role in supplying aggregate for key regional transportation infrastructure projects. To understand why massive machinery systems can operate reliably for decades under the harshest conditions, we must enter the heart of heavy mechanical production in Germany. This is not a typical workshop, but a place where engineering concepts are realized through an integrated cycle. From manufacturing pre-stressed concrete components to large-scale transportation infrastructure execution. The first technical highlight is the production line of pre-stressed concrete beams. The process begins in the rebar workshop, where automated cutting and bending robots handle high-strength steel based on digital blueprints. Absolute precision is mandatory, as this steel cage serves as the load-bearing skeleton for the entire component. Next, we witness the installation of pre-stressing strands. Each strand is threaded through a 45-meter-long hydraulic steel formwork system. Once the cage is in place, these strands are tensioned using specialized hydraulic jacks with a total force of up to 343 tons. This tensioning is designed to create a pre-compressive stress within the concrete, allowing the beam to span long distances without sagging or cracking under design loads. The concrete used for these components is an ultra-high-strength grade, produced with a unique formula from a fully automated batching plant. Liquid concrete is poured into the forms, while high-power vibration motors mounted on the formwork walls run continuously. This compaction process is vital to eliminate all internal air pockets, ensuring the concrete perfectly coats every strand in rebar, creating absolute density for the component. After curing under controlled conditions, these beams, weighing up to 80 tons, are lifted from the molds using double gantry crane systems. This is a display of physical power where massive blocks of artificial stone are moved effortlessly thanks to sophisticated hydraulic and hoisting mechanisms. The video then leads us to highway pavement engineering. The heart of this process is the new generation of asphalt pavers, working in sync with a fleet of steel and static rollers. Modern pavers can lay smooth asphalt layers over 10 meters wide in a single pass. Integrated laser sensors automatically adjust the height to ensure the road surface meets optimal flatness according to Eurocode standards. The extreme logistics aspect is also a technical wonder. To move components up to 47 meters long through narrow urban areas at night, engineers use specialized prime movers with independent steering multi-axle trailers. This system allows the entire 50-meter-long convoy to navigate tight corners accurately without hitting surrounding infrastructure. Positioning and erecting the beams at the site requires the coordination of heavy-duty crawler cranes. Every millimeter of error is monitored by digital total stations, ensuring the component fits perfectly with the previously constructed columns. This is a testament to German mechanical power and peak project management, where machinery replaces human labor in the most difficult tasks. Leaving the industrial sites in Germany, our journey reaches a grand symbol of modern infrastructure engineering: transoceanic suspension bridges. We stand before the Osman Gazi Bridge in Turkey, an engineering masterpiece connecting the two shores of Izmit Bay. At its inauguration, it was the world's fourth longest suspension bridge, with a total length of 2,682 meters, a testament to humanity's ambition to conquer nature and connect continents. Observe the two massive H-shaped pylons rising 252 meters above the sea, equivalent to an 80-story skyscraper standing tall in the swift currents. To keep these massive steel structures stable on complex geology and in a high seismic activity area, engineers had to perform a feat beneath the ocean. Massive caisson foundations, the size of a football pitch, were cast on land and then sunk into predetermined positions to serve as a solid base for the entire bridge. The project's greatest challenge was the installation of the main cable system. You must understand that this is not a simple steel rope, but a complex bundle of thousands of high-strength steel wires woven tightly together. The total tensile capacity of this cable system reaches hundreds of thousands of tons, enough to support the entire weight of the bridge deck and tens of thousands of vehicles passing above. The cable pulling process, known as the catwalk, is a dangerous task requiring absolute meticulousness. Engineers work hundreds of meters high, pulling each tiny steel wire across the bay with a sag calculated precisely to the millimeter to ensure the most even force distribution. Once the steel cable backbone was ready, the installation of the steel box girder segments began. Each segment is a massive hollow steel block manufactured with high mechanical precision at specialized factories. They are transported by barge directly to the site and hoisted using hydraulic strand jacks. The coordination between engineering teams above and below is the key to success. Even a slight error in calculating thermal expansion or wind speed could prevent the joints from fitting. The Osman Ghazi Bridge is not merely a transportation project, it is a logistics revolution, shortening travel time around Izmit Bay from 2 hours to just 6 minutes. But most importantly, the bridge is designed to withstand the most violent earthquakes thanks to its flexible yet extremely solid structure. From afar, it looks like a soft steel ribbon stretched across the sea, but inside is the combination of millions of labor hours, tens of thousands of tons of high-strength steel, and the pinnacle of human intellect. It is a symbol of enduring connection, opening a new future for international trade and proving that humans can turn the impossible into reality. Progress sometimes requires the sacrifice of the old. Through the time-lapse lens, we witness the swift demolition of the A452 overbridge in the UK to make way for the HS2 high-speed rail. The entire process, from laying protective road bedding to mobilizing a fleet of hydraulic excavators and clearing the debris, took place within just a 48-hour weekend. This was an all-out assault by heavy machinery, where seamless coordination between crews minimized traffic disruption, opening a new chapter for modern infrastructure. In Endicott, New York, the DRK horse demolition beast from the RCC series is showcasing fearsome mechanical power. This is a specialized concrete shear mounted on high-reach excavators. With blades made of ultra-hard alloy steel, the DRK horse doesn't just crush dense reinforced concrete, it snaps through heavy rebar as easily as paper. Under sophisticated control from the cabin, this shear reaches complex components dozens of meters high, making precise bites to bring down building structures without causing vibrations that affect the surroundings. This process is not just destruction, it is the first step of rebirth, where concrete and steel are sorted on site to be sent to recycling plants, continuing their life cycle in the structures of the future. Our journey today ends here. From the barrette piles driven over 72 meters deep into the burning sands of Dubai, to the DRK horse steel shears, crushing concrete in New York to prepare for a new rebirth, we have witnessed the limitless power of modern engineering. Every skyscraper, every transoceanic bridge you see is not just a soulless mass of concrete, but a living testament to the persistence, meticulousness, and infinite intelligence of humanity in the battle to conquer nature. Behind every square meter of urban space are millions of labor hours and calculations precise to the millimeter. If you are passionate about heavy machinery and want to explore the world of giant mechanics further, don't forget to subscribe and watch more videos on You Can Do TV. Join us as we continue to decode the industrial wonders across the planet. Thank you for watching and see you on our next journey.